Welcome back to Why This Universe. Today, we're welcoming back a very special guest to our show, Sean Carroll. You might know him as the man behind one of my favorite podcasts, Mindscape, or as the voice popularizing the idea of the multiverse interpretation of quantum mechanics. But aside from all that, Sean is also a cosmologist, and his research and writing about dark energy has been very influential in the field. So today, we get an inside scoop because we talk to him about how our understanding of dark energy has changed over the course of his career, and we dive into some of his earlier writing on the topic. If you want a primer on dark energy, whether it's before or after listening to today's episode, you can go back to episode 10 of our podcast called What is Dark Energy? Either way, stick around for a great conversation. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. Since the 1990s, cosmologists have known that our universe is not only expanding, but it's expanding at an accelerating rate. It's just getting faster and faster as time goes on. This, as far as we can understand, seems to imply that our universe must contain a lot of what we call dark energy. Unlike ordinary forms of energy like matter or light, dark energy doesn't appreciably dilute as the universe expands. So this means that as time goes on, dark energy comes to make up a larger and larger fraction of all the energy in the universe. And this, in turn, causes the expansion of space to accelerate. The density of dark energy might be completely fixed and constant. This is what cosmologists call a cosmological constant. But some cosmologists have also considered the possibility that the dark energy might evolve with time. It might get more or less dense as the universe's history plays out. And this kind of evolving dark energy is sometimes called quintessence. One of the people who did some of the important early work on quintessence is Sean Carroll, and he has graciously offered to talk with us today about this topic. Sean, as I'm sure a lot of you already know, is a cosmologist and a philosopher of science at Johns Hopkins University. He's also a prominent public intellectual, and he has a very popular and excellent podcast called Mindscape. He's also the author of some of my favorite books about physics, including From Eternity to Here, The Big Picture, Something Deeply Hidden, and recently a series called The Biggest Ideas in the Universe. Sean and I are absolutely thrilled that Sean has agreed to come on our show yet again. So without further ado, welcome, Sean, to Why This Universe.
Thanks very much, Dan and Shalma.
So, Sean, while you were a grad student, I think it was in 1992 at Harvard, if I recall, you and Will Press and Edwin Turner wrote a long article called The Cosmological Constant. This was, of course, well before we had any evidence for a cosmological constant or any other kind of dark energy, or any evidence that our universe's expansion rate was accelerating. Can you describe or recall for us what your thoughts about this topic were at the time, and even more generally, what the top thoughts of other physicists or consensus views among physicists might have been about the cosmological constant in the early 1990s?
Yeah, that's a great question to start off because it really does illustrate the sort of weird contingent wackiness of the history of science, right? I was a graduate student at the astronomy department at Harvard. Bill Press was a faculty member who actually, I had talked to and interacted with, but we hadn't collaborated with in any way. And Bill was asked by Alan Sandage, who was the editor of Annual Reviews in Astronomy and Astrophysics, to write a review article on the cosmological constant. I don't know why he was asked to do that. I know the reason why Bill was asked to do it, because Bill was sort of, in terms of Alan Sandage's mind, the best theoretical cosmologist who had not taken a stand on the cosmological constant or the Hubble constant or anything like that, right? So he was neutral. And at the time, right there at Harvard in the physics department, there was Sidney Coleman, the famous quantum field theorist, who had published a paper using Euclidean quantum gravity to explain why the cosmological constant should be zero. So very long story, very short, in quantum field theory, if you don't know any better, you can estimate the size that the cosmological constant should have, the amount of energy density there should be in empty space. And the answer is enormously larger than what you see. And we've known this for many, many decades now. And so this is called the cosmological constant problem? Why isn't there more energy in empty space?
10 to the 120 times too big, right?
Right,
Like
exactly
vastly, vastly, vastly too big. Yeah.
And so Sidney Coleman came up with an idea, very speculative, wormholes and Euclidean quantum gravity and things like that. And he made a very firm prediction: the cosmological constant should be exactly zero. So Bill Press, who was very good at, understanding the expansion of the universe and the growth of structure and things like that. He became famous for the Press-Schechter formalism back in the 70s and so forth. But he knew nothing about Euclidean quantum gravity. Oh my goodness,
Sure.
right? And so he knew that I kind of thought that stuff was cool. So my job, he asked me to collaborate with him and to write the sections on attempts to address the cosmological constant problem, including Sidney's, but also other famous ones. And then between the two of us, we soon realized neither one of us knew anything about the observational situation at an expert level. So we asked Ed Turner from Princeton, who was looking at gravitational lensing as a solution to that. And the three of us collaborated. But look, everyone knew that the cosmological constant could exist. There were very good reasons on the basis of naturalness, if you believe that that's something to take into consideration, to think it should be zero. Basically, in the space of theories you don't yet know, the thought was there's probably way more theories that would set this huge number to exactly zero based on some unknown symmetry or something like that we haven't discovered yet, rather than theories that would set it to a small number but not quite zero. That seemed very fine-tuned and unnatural. On the other hand, it's a free parameter you can use to fit your data. So there was a frequent occurrence in the history of cosmology when there would be some discrepant data and people would say, oh, maybe it's the cosmological constant, right? There was, too many quasars at a certain redshift, and maybe that was evidence for a loitering universe. Sure. And things like that. So we talked about all of that stuff, and we said, there's a line at the end of our paper that says the cosmological constant is an idea whose time has come and gone and come and gone again, and we expect that will continue into the future. So we actually didn't think anyone would discover it to be there. In some sense, it was perfectly ill-timed, that review article, because it was we barely mentioned either the cosmic microwave background or type 1 supernovae. Neither one of those ideas was really on the table.
So, but it obviously was a very impactful paper. I think it has like a few thousand citations.
Sometimes it's good to be before the moment that is there, because we certainly did, I should say Bill Press certainly did an amazing job of giving working cosmologists useful tools for figuring out what would the effects be if there were a non-zero cosmological constant.
So just a few years before you wrote that paper, Steve Weinberg wrote this attempt to discuss the topic. Describe what he said, and to what extent did that, influence your thinking at the time?
Yeah, Weinberg actually gave a series of lectures at Harvard, what are called the Loeb lectures. So they'll invite some famous physicists in to give like 5 lectures. And Weinberg chose the cosmological constant to talk about because he was Stephen Weinberg. He'd talk about anything and do better than anybody else. So he talked about lots of things, including Sidney's ideas about Euclidean quantum gravity, but also the idea of the multiverse and the anthropic principle. And I don't know which came first, but he ended up writing some separate research articles in addition to his lectures, which were later collected into a review article. And he pointed out, he was the first person, I think Andre Linde and some other people gestured towards this, but Weinberg, in his Weinberg way, sat down and did all the equations and worked it out. And he said, look, I don't know what a typical observer will measure, but I can guess that the number of observers is proportional to the number of stars, right, in the universe, and that's proportional to the number of galaxies. And I know enough astronomy to figure out, if I have a big cosmological constant, how will that affect the number of galaxies that are formed? So he did the calculation. He made a prediction, on average, the typical observer, if there is an ensemble of universes where values of the cosmological constant are just different, there won't be any observers in universes where the cosmological constant has its natural value. The natural value is too big. It prevents galaxies from forming. Most observers will be clustered in universes with a cosmological constant near zero, but there's no reason for it to be exactly zero. So he said loud and clear, if this scenario is true, we should probably detect a non-zero cosmological constant. And he estimated the magnitude of it, and he was within an order of magnitude of being right.
So, I mean, obviously that was extremely prescient. And, decades later, people like me would point back to that and say, like, maybe we shouldn't have been surprised. Like, seems like a really compelling argument. But at the time, when it hadn't been measured yet, you were just saying you didn't expect anyone to measure this. But Weinberg should have told you should expect somebody to be able to measure this. So did Weinberg's argument not hit home at the time in the way that it would seem like it should have later?
Well, let's skip ahead in history a little bit, because it's illuminating. In 1998, when we did have observational evidence that the universe is accelerating, remember the theoretical physicists who were thinking about quantum gravity and things like that, they were struggling with why the cosmological constant wasn't much bigger. And if you are in love with supersymmetry, which many people are, or string theory, which many people are, it turns out it's easy to explain a negative cosmological constant. It's very, very hard to explain a positive cosmological constant. Indeed, Ed Witten wrote a paper saying, yeah, there can't be a positive cosmological constant. We all know that. And then they discovered
this is anti-de Sitter space versus de Sitter space, right? Yeah,
that's right. And so, but just in general, anti-de Sitter space, it turns out to be super useful as a toy model thought experiment for string theory. But even in a attempt to be phenomenologically realistic, it's just very hard to get a solution to string theory with a positive cosmological constant. And so, but then they discover that there is a positive cosmological constant, or maybe dark energy, and we can get maybe some dynamics. Sure. We can get into that. But that kind of shook up the string theorists, right? This was I think the first and only time when the course of string theory research had been dramatically affected by an observational result.
Yeah.
And so people in the string theory land, starting with Raphael Bousso and Joe Polchinski, and then working up to people like Lenny Susskind and others, said, okay, are we sure we can't get a positive cosmological constant in string theory? And they found, actually, yes, maybe you can, but if you can do it one way, you can do it 10 to the 500 ways, right? And so this was the birth of the string theory landscape. And suddenly you had this idea of a multiverse with very different values of the cosmological constant, et cetera. But all that is circa 2000. When Weinberg is writing in 1988, none of that was there. Right. So the idea that maybe you could have different universes with different values of the cosmological constant was certainly known as a speculation, but there wasn't any more or less popular scenario that would actually lead to that. So when Weinberg says, if you have this ensemble of universes with different values of the cosmological constant, you can explain it away, everyone, including Steven Weinberg, was like, yeah, but we don't. So that seems very implausible. So it did not take the community by storm at the time.
So what about, so we didn't have the string theory landscape ideas yet, but we had ideas having to do with eternal inflation. So in certain classes of inflationary cosmology, you end up with an infinite number of causally disconnected spaces or universes, if you will. And you could imagine those might have different values of the cosmological constant problem. Were people thinking about this in this context? Even if you don't have the string theory arguments?
People thought about it, but it just wasn't that popular. I mean, the idea of eternal inflation was there. The idea of eternal inflation goes back almost to the idea of new inflation. It's 1982 or so. But a lot of people thought of it as something that Andre Linde did in his spare time, right? Drawing cute pictures of many different universes being created. There was no programmatic way to say that in those different universes, you should have a different value of the cosmological constant. You could make it up, you could imagine it, but there wasn't any motivation for doing so. And also, people weren't, you got to remember, I don't know if there's anyone out there in the audience as old as I am, astronomers didn't even believe in inflation in the late 1980s. Right. Because look, inflation only made two predictions. One is that the universe should be spatially flat. And the other, what was the other one? That there should be certain perturbations in the cosmic microwave background. And they hadn't discovered either one of those, right? So physicists love inflation at the time, but astronomers going, along their way just thought, no, the omega matter is 0.3. We live in an open universe, prove me wrong.
Yeah, like by 2000 or so, all of those predictions of inflation had been borne out, but
That's right.
Not yet. Yes. Yeah, good. All right. So 1998, first evidence of accelerating expansion and therefore of some sort of dark energy, cosmological constant or otherwise. And then in the year 2000, there's a new article appears by you again, Sean, this time a single author paper. You don't have those same co-authors, but it has the same name, the cosmological constant. So new article, same title. What changed about your perspective? Obviously, it changed that we discovered accelerating expansion. So, that goes without saying. But what, on a theoretical perspective, what changed about your thinking in those 8 years about the cosmological constant?
Yeah, I think that there were two major theoretical shakeups when we discovered that there was a non-zero cosmological constant. One was that we had all these really good naturalness arguments that completely failed us.
Yeah.
And I was a believer in those naturalness arguments. Like you would have won a lot of money off of me.
You would have thought it should be zero.
I would have predicted it would have been zero.
Okay.
And by the way, for our listeners out there, there's one other famous example in physics of a naturalness argument that has motivated a lot of people, which is the hierarchy problem in particle physics, which led a lot of people to believe very strongly, again, including myself, I'm just being honest here, that we would find a whole bunch of new particles at the Large Hadron Collider in addition to the Higgs boson.
Yeah.
Guess what? We didn't do that either. So I do believe
I'm in that camp too.
We should, as a field, I don't think we've quite reckoned with this. Our complete failure, our 0 for 2 batting average in this naturalness argument thing. I still believe that naturalness arguments are worthwhile doing, but clearly we're not doing them right. And so there needs to be some rethinking there. But so that was one thing that happened I put a lot of arguments in the 1992 paper. Here's why it's going to be zero. I can't put those in the 2000 paper, right? Because it's apparently not. But the other was, for better or for worse, the cosmology community took that lesson to heart and said, look, we all fell for this naturalness argument that says the cosmological constant should be zero. Now there's another naturalness argument that says, again, I'm partly responsible for promulgating this one also, that says it's much more natural to have just a cosmological constant than some dynamical rolling scalar field or something like that, because that would be very easy to detect. There would be all sorts of experimental tests. It would be very unnatural for it to hide from us. But the attitude in the community was, look, we were wrong about that once. We should be open-minded this time. So even though we have this new observation of the supernovae, et cetera, and we have a perfectly good explanation for it that was given to us by Einstein 100 years ago, maybe we should be a little cautious. Maybe we should be a little open-minded, and maybe we should do our due diligence, think about other possibilities. And as you know, enormous amounts of effort and dollars have now been spent on trying to test whether or not the dark energy actually is a cosmological constant or not. And whether or not it's even dark energy at all. Is it modified gravity or something like that? So in the 2000 paper, it was still a little early to actually say what people thought about that, but I did talk about those possibilities.
Good. So you touched on this a little bit already, but I think you used the phrase rolling scalar field. But maybe you can kind of sketch out for our listeners how a dynamical dark energy, how a quintessence model might work, what its components are, what are basic elements and how do they work together?
Yeah, this is something that the theorists were very well equipped to think about because they all knew about inflationary cosmology. Inflation says in the very early universe, there was a field pervading all of space, some scalar field. We don't even know what the identity of it is. We call it the inflaton because it's the field that makes inflation happen, but we don't know.
Just a placeholder. Yeah.
Right. Alan Guth, when he invented inflation, thought it was the Higgs boson for grand unified theories, but that turns out not to work for various reasons. So there's a scalar field out there, and scalar fields have sort of three kinds of energy associated with them. They have kinetic energy when they're changing with time. They have gradient energy when they're changing with space. The value of the field is different from one point to another because a field exists at every point in space and time. But then they also have this potential energy, this energy just from the value of the field, not from how it's changing in space or time. And in particular, if you have a situation where it's not, the scalar field is not changing very much in either space or time, it's just sitting there with potential energy, that acts very, very much like a cosmological constant. It acts like a persistent, constant, smooth energy density pervading all of space. And this kind of idea in the very, very early universe is what gives rise to inflation. So when we discovered the accelerating universe in the contemporary world, it was very simple for theorists to say, well, maybe there's another kind of scalar field that is not exactly constant, but only very slowly changing that would mimic the effects of the cosmological constant. And it was dubbed quintessence. And then it was sort of subsumed into this bigger idea of dynamical forms of energy and now dubbed dark energy.
As a side note, the word quintessence goes back to Aristotle, right? Is that?
Well, it goes back to the ancient Greeks. Okay. It was the fifth element. The Bruce Willis movie, Mila Jovovich, the fifth element was named after quintessence. Earth, air, fire, water. Quintessence was the heavenly element.
Other than it just being some new exotic stuff, does it, the modern cosmological quintessence, does that have any connection to what the ancient Greeks had to say about quintessence?
It's in the sky.
Yeah,
that's the only connection.
Yeah, right. All right. So if you have a scalar field that's slowly evolving, giving us some sort of dynamical dark energy, well, anytime you have a scalar field, you also have a scalar particle. That's the excitations of that field. And to evolve slowly, that scalar particle has to be really, really light. This, of course, leads to things you might observe. Maybe tell us a little bit about that.
Yeah, just to put a personal spin on it, in 1998, when we discovered the dark energy, discovered the acceleration of the universe, I was struggling to find a job. I was a postdoc, right? Yeah. And I was not working on any of the hot topics in physics at the time. And I was just smart enough to go if I want to get a job, I have to become the world's expert at something other people care about. It's a natural request. I was already the expert in the cosmological constant and dark energy, but no one cared about that. Suddenly people started caring about it. And so I became a hot property on the job market through no special effort of my own. But I did sit down and try to think about this idea of dark energy, et cetera. People were basically trying to solve two problems. The idea of dynamical dark energy wasn't just, at the time, in 1999, it wasn't simply, well, maybe dark energy is dynamical, let's explore it. There were aspirations to help solve the naturalness problems that were left over. You still have the naturalness problem of why the cosmological constant is so small, but now you have an additional naturalness problem. Why isn't it quite zero, and why is it of the same order of magnitude as the energy density of matter in the universe, right? Matter is 0.3 of the universe, dark energy is 0.7. Those are not the same numbers, but to cosmologists, those are equal. Yeah. Especially when they change very differently with respect to each other over time. The dark energy is almost constant, the matter density dilutes away quite rapidly as the universe expands. So this is called the coincidence problem. And so people tried to use the dynamics of scalar fields to address the cosmological constant problem, why is it almost zero, and the coincidence problem, why is it equal to the matter density today? None of those attempts really worked, I have to say. So today, we're still looking for dynamical dark energy, but it's more like, well, maybe it's out there, it would be worth looking for. And what I pointed out, I knew just enough quantum field theory to know, look, you can't just have nearly massless scalar fields lying around willy-nilly like these cosmologists like to invoke. There are rules to this game. We have effective field theory, which says that I don't know what all the rules of fundamental physics are, but at low energies, I have a very reasonable set of expectations. If I have a very, very low mass scalar field, it should, number one, why do I have a very, very low mass scalar field? The mass of the Higgs boson, which, remember, to particle physics is unreasonably light,
Right.
is 100 billion electron volts. And this new boson we were positing to be dark energy is 10 to the minus 33 electron volts. So if 100 billion,
very light.
Yeah,
Yes.
if 100 billion is small, then you got to really work to explain 10 to the minus 33. And then if you do it anyway, you say, no, I just insist on having a very light scalar field. Why haven't you found it yet? Why haven't you noticed it in experiments? It should give rise to a new force of nature. It should push around the effective values of the charge of the electron and the mass of the proton and things like that. And we have all sorts of experimental evidence that none of this is actually happening. So I wrote a little paper explaining that all these were problems and pointing out that there is one scenario that eludes them. You can invent a symmetry that both keeps the mass of this dark energy boson very, very small and zeroes out all the interactions that it would have with ordinary matter, leaving just one, which is this pseudoscalar birefringence interaction. I don't know if you want to go into that, but at least it gave a target for cosmologists to actually look for a direct interaction between photons and dark energy, which is very exciting.
And they're still looking for that in the CMB today.
They're still looking. There's even like a 2 sigma claim that they found it, but it's going to take better data to know for sure.
Right. Good. All right. So that brings us to the present era. Earlier this year, something called the Dark Energy Spectroscopic Instrument, or DESI for short, released its first set of data. And this data might have something to say about these questions related to dark energy. Maybe, Sean, you can tell us a little bit about what DESI does, what it's measuring, and what it might be telling us.
Yeah, as soon as these two groups studying supernovae back in the 1990s, the High Redshift Supernova Team and the Supernova Cosmology Project, found evidence for the accelerating universe, of course, people's eyes lit up and said, okay, let's do it better, right? Because this whole idea of finding bushels of supernovae was not something that was expected to work back in the 1990s. And even if you found them, would they really be standard candles, et cetera? So once they had proven that it did work, then of course you want to do it better. You want to have a better set of observations. And you realize that it's not just supernovae that you can look for. Look at gravitational lensing, look at the growth of large-scale structure, look at the cosmic microwave background. So there's all sorts of different techniques. And DESI, I think that DESI is mostly gravitational lensing, is it? Or is it supernovae that they're looking at?
So they're looking at the distribution of galaxies. They're making a big 3D galaxy map, and also quasars, all spectroscopically. And with that distribution of these things, they can look for the imprints of baryon acoustic oscillations, which give us
baryon acoustic oscillations, right.
Beautiful measurements of distances over tens of billions of light years.
Yeah, the good news for the working cosmologist is that we, from the microwave background radiation, have a pretty good idea of what the perturbations in density were like a few 100,000 years after the Big Bang. And then we have a pretty good theory, namely Einstein's theory of general relativity, for how those perturbations grow over time to the present day. And that growth is going to be affected by the dark energy and its evolution, as well as the density of matter and radiation and things like that. So it's a huge treasure trove of data that we can fit our models to. And the most recent results from DESI, DESI, are that the best fit has the dark energy changing by a little bit, right? And by changing, I mean the density, the ergs per cubic centimeter, gradually diminishing over time. And by the way, I shouldn't leave out the fact that this worry on the part of string theorists from the 1990s that it was hard to fit a positive cosmological constant into the theory, even though a bunch of people have explored the possibility, there's a whole another bunch of people who are string theorists who still don't think it works, who still don't think you can get a positive cosmological constant in string theory. So they think that the evidence that we have the universe is accelerating probably means that the dark energy is dynamical, that there is some slowly rolling scalar field out there. So they're all happy about this new hint from DESI. It might even be right. I don't know. I mean, you can't get too excited about these very tentative one experiment kind of results. You have to wait for someone to say that it's confirmed.
So maybe it's going to turn out that the 1992 version of Sean Carroll was right in thinking that there probably is a zero cosmological constant. But on top of that lack of vacuum energy, there's some sort of rolling scalar field that gives us some sort of dynamical version of dark energy, like the kind that the DESI data is hinting at now.
Yeah, and if the 1998 version of Sean Carroll is right, then we'll be able to see this dark energy interacting with photons in an interesting way. But look, I'm trying to be very honest. Like, my track record is spotty here. I wouldn't give any betting advice to anyone on the basis of what I've thought at different moments in time. Like, we all do our best at every one moment, and then nature is going to decide.
I mean, I was in high school in 1992, so I didn't have any opinions on the cosmological constant problem. But if I had, some later version of me had been put in that situation, I'm sure I would have got it wrong. Nothing about how it played out was particularly foreseeable to me.
There were a scatter of papers. Well, let me tell this one story. In 1997, so the year before the supernova results were released, we discovered the anisotropies in the cosmic microwave background. The COBE satellite back in 1992 did that, but it didn't give us a lot of quantitative information about the whole spectrum of perturbations, right?
Mm-hmm.
I mean, it was really just we discovered one number,
right.
And there was, again, once that happens, there's now a rush to start doing that better. And we finally started doing that better in like 2000, 2001, et cetera. But in late 1990s, we were gearing up to better measure the cosmic microwave background, but we hadn't done it yet. And so we had a conference, Phil Lubin at UC Santa Barbara, where I was as a postdoc at the time, organized a conference on measuring cosmological parameters using the cosmic microwave background. That was the exciting thing to be thinking about. And I, as a local postdoc who didn't really work on these things, was invited to give a talk on measuring cosmological parameters using everything other than the cosmic microwave background. So I could provide some context to everybody. So I was not an expert on that either, but I was enough of an expert that I could read the papers and do it. So I really took it seriously, and I sat down and read a whole bunch of papers. And I came back and gave my talk and said, look, we theorists, such as myself, we have a favorite model. The model circa 1997 was the universe is spatially flat. Okay. Omega equals 1 in the parlance of the day. The density parameter of the universe is 1, giving us a spatially flat universe, the critical density. The cosmological constant is 0 because it's unnatural for it not to be 0. The matter density in the universe is cold, dark matter. Okay. And this is sort of the cosmologist's favorite model. The density perturbations are scale-free. They're the same at every different wavelength that we can look at. And I got up in my talk in 1997 and says, that model is wrong. That model cannot fit the data. Plenty of different little pieces of evidence here and there are saying in different ways, but they're saying exactly the same thing, namely that model can't be right. And maybe it's because the universe is spatially open, right? Maybe there is spatial curvature. Maybe it's because there's a cosmological constant. Maybe it's because there's a tilt in the spectrum, so there's more power on large scales than small scales. Maybe it's because dark matter isn't cold. Maybe it's warm, or there's a mixture or something like that. So we had lots of options on the table, and we didn't know which one it was. But in December 1997, I was on the record as saying something big is wrong about our favorite cosmological model. And then 2 months later, we found out what it was.
Wow. I know there was a meeting that 95 or 96, and I think it might have been at Fermilab or University of Chicago. I'm not sure which. And there, the opinion was that the cosmological constant would be non-zero. But I wasn't there, obviously, but people certainly recalled that meeting who I knew well, who thought they had good reason to think that, before the famous 1998 events.
That's right. There were definitely a couple of papers, a handful of papers, I should say, of people pointing out quite correctly, look, we can solve a lot of problems if we just have a non-zero cosmological constant. I would say I haven't read those papers in 20 years, but I would say that if we went back and read them, probably none of them say, therefore, there probably is a cosmological constant, right? They were hedging their bets at the time. They would say, look, I don't know what you want to do about it, but it sure would help us if the cosmological constant were not zero. That's one step below saying, therefore, it probably is non-zero. That was a leap I didn't hear anyone quite be willing to make.
I remember one of my colleagues, it wasn't at that meeting, but he's a numerical cosmologist, Nick Nedden. He was around during that time. And he said in 1997, I was running cosmological simulations. And in 1999, I was running cosmological simulations. And I was using the same parameters. I had, cosmological constant in both of them, at least he was bothering to run those simulations with a particular value.
Well, it's also very useful for the people listening to understand that the discovery in 1998 that the universe is accelerating, which we attribute to the cosmological constant, that was a big deal, right? Nobel Prizes all around. But there were two reasons why 98% of the community accepted it right away. One is that, of course, there were two separate groups who were competing each other that both got the same result. Okay. But the other is it instantly made everything make sense.
Yeah.
We had a theory that explained it. There were other observations about the age of the universe. Remember, that was an issue. Even what we knew about large scale structure at the time, many things got easier if you had that cosmological constant. Many other subsequent teasers about new results, like the DESI result, like the Hubble tension that we now struggle with, many different things, they don't make anything easier if they're true, right? Like, it's hard to explain them theoretically. There's no other data that they explain. It's just an anomaly that is kind of sticking in our side, and we don't know what to make of it. So we're going to react differently to different experimental results. So sometimes it's like, oh, yes, of course, I should have known that. Other times it's like, prove it to me.
Sure. So here we are in 2024. These DESI results, when you combine them with things like measurements of the cosmic microwave background and supernovae data and all this, suggests that maybe at the 3 or almost 4 sigma level, there could be some time variation in the dark energy. Now, I don't know about you, Sean, but I would say most of our colleagues don't put a ton of credence on something that's a 3 sigma result. Those kind of come and go. That you might bother to check them out, but you wouldn't, bet your house on them. 4 sigma starts to look pretty intriguing. And 5 is, of course, the gold standard for discovery. Right. So that gives the listener an idea of where we stand. I don't think anybody actively believes DESI's discovered that dark energy evolves, but they've gotten a lot of our attention, and we're going to pay some attention to the next measurements as they come out.
Yeah, I think it's absolutely true. Every word you said is true, except you could also add that, like, if we're doing psychology, then 1 or 2 sigma would be amazing. So we're
yes.
fortunate enough to be in a field where we can at least imagine a 5 sigma result someday. And I think, people don't want to hear it, but I think that's the attitude. We can be patient, right? This is not the only effort to measure the time dependence of the dark energy. Right now, gun to head, I would still bet the dark energy is constant. But I would not bet it at 100 to 1 odds, right? So I think that there's a substantial fraction of possibility that it's not. And if it's not, that's a hugely important result that absolutely fundamentally changes how we're trying to explain this puzzling phenomenon. So I'm cheering on the people who are out there trying to make these very difficult measurements.
So I have one more question. We've mentioned that the dark energy could be changing in time. Does that mean it's also possible that it could vary across different parts of space as well? So that, one part of space is expanding with a rate and another part of space is expanding with a different rate?
It's 100% possible. In fact, it's almost inevitable that it will be. But for various dynamical reasons, it doesn't want to be that different, right? It costs energy for it to be that different in place to place in space. The rest of the universe is already pretty homogeneous, so there's no reason for a lot of energy to be dumped into the dark energy field to make it be different from place to place in space. So, think of it this way. If it is a field that has kind of a particle in the most straightforward way, the mass of that particle is 10 to the minus 33 electron volts. So the Compton wavelength of that particle is the Hubble radius. It's the size of the universe. You can't squeeze that particle into a box smaller than the size of the universe. So it doesn't want to coalesce or coagulate in some region of space like dark matter does or ordinary matter.
I see. I guess that does leave open the option that the universe beyond the observable universe is really much bigger than we could imagine. And
that's very possible, yeah.
Maybe we just happen to be in just a Hubble radius where we have this positive cosmological constant.
Yeah, or dark energy density evolving with time. Like I said, we have very good naturalness arguments, but they keep steering us wrong. So I think we should still keep developing them and thinking about them, but we can't let them guide our thinking too severely.
Thrilled to have you on, Sean, and I'm a big fan of the stuff you do. So this is a treat for me. Thanks.
Mm-hmm.
All right. Thanks, Dan. Thanks, Shalma.
Why This Universe is produced and edited by me, Shalma Wegsman, and our co-host is Dan Hooper. Dan is a professor of physics at the University of Wisconsin-Madison and the director of the Wisconsin Ice Cube Particle Astrophysics Center. If you like our show and you want to support us, you can join us for as little as $3 a month on Patreon. There you can also get access to exclusive Ask Us Anything segments where you can directly ask Dan and I any of your questions on physics or whatever else. And to find that, just go to patreon.com/whythisuniverse. As always, thanks for listening.